the estimating predictive performance of GPs, selection-induced bias, model averaging, mention ARD again, so those who were yesterday know this, projection predictive methods, and it's okay, yeah, the outline misses now also then the model combination there. Why I wanted to talk about this are especially these two things, variable selection. So if we are using Gaussian processes for these regression, classification, survival analysis, prediction tasks, for example, in survival analysis, there's different things we know about the patients. And with the GPs, we can just put everything in, but then it would be easier to explain these models if we can choose just the smallest possible set which can give the same predictive performance as all the available information. Automated statistician, I mentioned it also yesterday, doing combinations of different kernels. For example, if you would give the birthday data, it would automatically try to find different components needed to add there, and then give a report explaining these different components. And then it means that again we have this selection problem. And then, of course, with the variable selection, instead of variable selection, we should just put everything there, use relevant prior information, and integrate over all uncertainties. And it's then just, and for example, so Radford-Neal, there was a NIPS 2003 feature selection competition, where the competition organizers thought that they would find methods that you could improve the performance by feature selection. And Radford-Neal demonstrated that using Bayesian methods with all the features from 500 to 100,000, you don't need to do the selection at all. Just integrate over all uncertainty. But then we can improve model interpretability, also reduce measurement cost in the future if you think about these healthcare applications. Of course, there are more and more biochips which measure a lot of different things from blood. But sometimes it's even that taking the blood sample, the time the nurse uses for that can be the cost, the dominating cost. And then we can reduce the measurement cost if we choose the smaller set. And might be also reducing prediction time. Some cases we might have also timing issues, time constraints for the birthday example is good example that we would like to find combinations of different length scale processes, combinations of different period length processes. In that birthday example, I did manually this work. Of course, it was also easy to know that there are yearly period and weekly period. But then one example where this kind of automated statistician was used was the sunspot activity. There's no period in a way known beforehand, and so on. You know, the GP, ARD, the toy example. Is there someone who wasn't there yesterday? No? Or one more? Okay, so I can skip that. So instead of looking at then the ARD, I like to look at the predictive performance of these models. So that if I have two different choices, like which variables to include, if they have the same predictive performance, then I would choose the one which has less variables. And I briefly then talk next about that we can use cross-validation. which gives an almost unbiased estimate of the predictive performance, and for GPs, how we can compute that fast. And the benefit of the cross-validation is also that it's we don't need, it's M-open, where we assume that none of our models are the true model, which would be unlikely in these very complex phenomena we are modeling, like humans and survival of humans. So okay, and this leave one out, I'll come back to in these other parts also, and so briefly going through this. So we first look at the leave one out, where we look at the conditionally on hyperparameters. And we would like to know what's the prediction for left out observation given data where we remove the one observation. And we look how to compute this. But then we can also then take into account that we don't know the hyperparameters, and we can then compute also the leave one out when we integrate over the hyperparameters. Here the theta are covariance function parameters, phi are likelihood parameters like the noise variance. If we consider the case where we have not yet seen the ith observation, then we can use the previous posterior as a prior, and then we get the new observation and combine them using the Bayes rule. So this was, if we would have observed only now the n-1 observation, so this is our posterior for the latent, then we get the new observation, and then we get the updated posterior for the full. Now we can then rearrange the terms so that instead then rearrange the terms, we can find out what would be the leave one out posterior. And then if we now integrate both sides over fi, rearrange the terms, we get these leave one out prediction given the data, and this one. And now in some cases it turns out that we can compute then this, so some cases we can compute this exactly. And since we are in a Gaussian process workshop, and the Gaussian process with finite data is just a multivariate normal, we can use the properties of the multivariate normal, and turns out that we can find out that conditionally on the hyperparameters and the Gaussian likelihood, this is Gaussian, and we get Gaussian with these parameters from the properties of the multivariate normal. And that's fast then to compute. In case of expectation propagation Laplace, we replace now the exact posterior with our Gaussian approximation, and Alan just showed you, talked about those, and Opper and Winter showed 2000 that in case of EP, this is also gives first order consistent leave one out estimates. Nice, so we get them actually as a free byproduct from EP. And then we showed in this 2014 paper that this is also holds for Laplace. And you can just think that in both in EP and Laplace case, we replaced now the non-Gaussian likelihood with the Gaussian approximation, and in these two cases we know what the Gaussian approximation for the likelihood is, and then can use again the multivariate normal properties. And so here these are the kind of the approximations, the mean and variance approximation for the likelihood term. This likely holds also for VP. We hadn't looked at it because we don't like so much VP. It underestimates the variance, and you can get the same speed with EP faster with Laplace, although then in some cases Laplace fails compared to EP. Okay, so this was with the fixed hyperparameters, and then, as I talked yesterday, we need to integrate over hyperparameters to do full Bayesian inference. If we would just optimize the hyperparameters, we can, of course, compute the leave and out results, but they would be optimistic. And again, if we have a lot of data, I mentioned that you can replace the integration with optimization. But I've seen several cases where there's clear difference. For example, survival data, even if we have quite many patients in a study, there's usually a small amount of patients which get an event, and also otherwise in the survival data, the likelihood is quite weakly informative, and even with the lot of data, it's really noisy, and then we have a lot of uncertainties about relevance or the nonlinearity of the different variables. I showed you HMC and just one figure about the CCD also yesterday. And now we can do this hierarchically, so that we can use the conditional results and then use importance sampling for hyperparameters. So that if here now, if we have these MCMC samples, these are the conditional leave and out terms, and then we take the average sum with weights, and these importance weights happen to be, again, proportional to inverse of this term, which we get out from these fast conditional leave and out computations. And the leave and out predictive density then simplifies to this. Variance of importance sampling can be reduced by using Pareto smoothed importance sampling. We have a paper about that. And you can use the importance weighting also when using this deterministic CCD method. And in our paper about the fast leave and out for Gaussian latent variable models, we have then results showing that all these work quite nicely. And so far, so the message was that we have fast way to compute estimate of the predictive performance of Gaussian processes. We can use that estimate then to compare models, but I can recommend it only if you have small number of models, because even if this was unbiased estimate for a single model, if we use now that estimate to make a selection, we are then using the data again, and we are in a selection process fitting again to the data. And this problem is bigger more models we have. We could estimate the performance of the selection process itself by adding another layer of cross-validation. And this kind of nested cross-validation has been used, but the problem with that is that we can only know again that how much we overfitted, but it doesn't remove this problem of overfitting in the selection process. And there's a paper showing these results, figures now. These were with the linear models. Variable selection, there's 50 variables. The dashed line shows the full Bayesian model where we include all the variables, we have a suitable prior and integrate over all uncertainty, and then we know that we should not be able to do better with a smaller model. We then start doing backward selection so that we remove one variable, compute the predictive performance, and do this for all variables, and choose the slightly smaller model with the best predictive performance. Again, remove from that one at a time, the variables still there, choose the best, and so on. And if you look at this leave-and-out predictive performance estimate, when we have small data, it goes up. It thinks that it can find better models than the full model. But the black line shows the performance compared to independent test data, and it goes down. So we are severely overfitting. Here's a combinatorial explosion of models, how many different models there are, and it can choose combination of covariates such that the noise in the covariates can be chosen so that it can fit better and better just to this training data. We can see that the problem gets there's less problem when the number of observations increase, and if we would continue, this would all the time getting smaller. But we have often cases where we don't have so much data. Here's another examples. There was 100 covariates going to up to 400 observations, but this also shows that it's not just a cross-validation, it's also different information criteria and also marginal posterior probabilities which are related to Bayes factors and so on. And then the bottom line looks good, and then I'm talking about that soon. More examples from different datasets. This projection predictive method, the decision theoretic idea can be tracked to Lindley's 1968 paper. And even as Lindley was very prominent figure in Bayesian statistics, it's surprising that these decision theoretic ideas did not get more popular. There were some people every now and then remembering these, being able to publish something, but then again not getting widely used. The specific computational version we are also using, it's close to this by Cotis and Robert, Dupuy and Robert, approach for generalized linear models. And as you could see from the figure here, you can see that it really helps in a way that we don't get overfit. The general idea is that we first form the full model with all the variables and use all the available prior information we have and use best possible inference methods to integrate over uncertainties. And then we want to find a smaller model which is easier to explain. But now this submodel is obtained by minimizing predictive Kullback-Leibler divergence to the full model. And then for a given number of variables, choose the model with minimal projection discrepancy. So now we are not using data anymore in this selection phase. We use the data to form the full model, but after that we condition the inference, the selection process on this full model. Because we are now using, instead of just kind of the finite set of observations, we are using the predictive distributions of the full model. We get less variance, and because in a way we are now blocking the flow of information from the data that we are not looking at it anymore, we are just looking at the full model, we don't overfit the data, and also it turns out that we are able to preserve information from the full model. So we get better submodels than if we would take the same submodel and then do the posterior inference conditionally that submodel and the data. So you can also draw a figure. So if we have theta 1, theta 2, we would have some posterior for them. And then we would like to do this predictive distribution as I have there, y tilde, given data. I would do this. Okay, so I'll just add now different thetas there. So py given theta 1, theta 2, and over the posterior distribution of p theta 1, theta 2 given data, t theta 1, theta 2. And this is what integrating over both dimensions. Now we want to find out what would be the best distribution for theta 1. That if we use just the theta 1, and if now we want to then compute p tilde conditional d, but now the integral is only using theta 1. Oops, now this is the q. No. This is p and this is q. Okay, not like this. So instead of integrating over both theta 1 and theta 2 based on the true posterior distribution, we want to find out q or distribution for theta 1 so that these two would be as similar as possible. And in the variable selection case, it's also so that what if theta 2 would be 0 in the linear model case or the generalized linear model case. And so we have now the optimization problem. So this is now this one. and this integral is now this one. And the KL divergence from the full model to the submodel with the projected distribution minimize this KL divergence, and then for separately for each the xi combination. So it's optimal projection from the full posterior to sparse posterior with minimal predictive loss. So we lose predictive information as little as possible. Practical implementation is that we have posterior draws for the full model, and the predictive distribution for the full model is then just this. It's now difficult to compute the KL for this, and now the Coates Robert, what they proposed was to change then the order of integration and optimization, so that we look at the predictive distribution given one sample, and in generalized linear model case and the Gaussian linear model case, then it's easy to compute the scale divergence and then to optimize the parameter to minimum, and then we are projecting each sample separately. And it turns out that even if we change this order, these projected samples form a good approximation for what we want. And so we get approximate draws from the projected distribution. And for this Gaussian linear model, we can compute these analytically. And in exponential family case, we have a task which is the equality dividing the maximum likelihood parameters for the submodel with the observations replaced by the fit of the reference model, which has also fast iterative algorithm for that. Then with the GPs, this is a little bit more difficult, because the parameters of the likelihood are essentially the latent values and then the likelihood parameter like sigma. Without constraints for the latent values in the submodel, the solution to the minimization problem would be just that use the original latent values. So we are not actually then learning anything. So we need to look at our focus was in GPs would be then on the covariates and how the covariates come into picture. We are using them to construct our covariance matrix. So instead of looking at the Fs directly, we have to look at the constraint covariance matrices. And so we require constraint that the submodel prediction satisfies the usual GP predictive equations. And so we had first the full model, and we get the Gaussian distribution for the latent values. And now we want to then find the Gaussian with the constraint mu and sigma. These mu and sigma, so this is the predictive distribution from the full model, predictive distribution for the constraint. We said that these have to be in the form of the prediction equations for the GP, and now we just have to how we choose the projected K. Oops, it seems now I don't remember whether I had the further part that then now the reduced K, for example, if we remove a covariate, then we have one length scale less, and then we, for example, project the length scale samples to the subspace so that this projected covariance matrix would then produce such predictive mean and covariance that this KL would be minimized. And here's what happens when we use the projection prediction. It can predict the relevance of each of these variables just as it should. In variable selection, usually not feasible to go through all variable combinations, so we've used forward, backward selections. Yes. Now with the GP, there's a Boston housing, 13 variables, automobile 38, and crime 102 variables. Dashed line is now the full model with all inputs and using MCMC to sample hyperparameters. Yes, what if we order the variables based on ARD? And here's the red line is the performance if we use now the projection. And it's not just about in which order we add it, it is also that we get better performance because of using the projection. And you can see that when we get more and more variables, there's bigger and bigger difference here, and we can find smaller models which achieve the same predictive performance as the full model. For the non-Gaussian likelihood, we can then make the projection conditional on Gaussian likelihood approximations, so the same approach. So now we get better models. This is still a bit slow, especially if we are using forward selection and there's large number of covariates. We need to form these GPs computations many times, and you know about the problems of the scaling of GP with number of observations. We are now just, so we have preliminary results for an approach where we can find good relevance estimate for the variables so that we can, instead of doing the forward selection, we can just right away order variables and then just do the prediction in pre-ordered for the pre-ordered variables, do the projection for the pre-ordered variables. So summary for if you want to make model selection really carefully, then do the inference for the full model first, and then use the projection if you need smaller model. In here I had the examples for variable selection, but I'm certain that this kind of automated statistician trying out different kernels will overfit too if there are kind of too many choices what kind of kernels it can put there. It will overfit, and also it's possible then that it adds too many kernels in that way that it's not anymore easy even to interpret what all kernels do. And as I discussed, there's the identifiability issue also, that there's interplay between these kernels, and then if you are not careful with the priors, you get other problems too. Now, in this variable selection, the full model, we used MCMC to sample over the hyperparameters, so there was the length scales for different dimensions. But then in more generic case, how we combine different models. And this is now, again, especially aimed for those thinking about automated statistician. I know there are some in the audience. And now next, I talk about then combining different models and how to do it, again, fast. So I'll talk about usual solution, the Bayesian model averaging, Akaike type weighting, and stacking. So we could use reversible jump MCMC, so sample both hyperparameters and models. Doable, but can be slow. We could use approximate marginal likelihoods of models. So if, like in the automated statistician based on GPs, we would use the EP or Laplace or VB approximations, and from those we could get the approximate marginal likelihood and then only do MCMC jumps on the model space. But it's still, when we have a lot of different models, it's slow, this kind of just jumping from the model to other. And in addition, we have a problem that it's not so easy to approximate the marginal likelihoods when we need to integrate over the hyperparameters of the covariance function and the likelihood parameter. So if you now think that we want to compute the marginal likelihood for certain kernel combination, and that marginal likelihood then required the integration of the latent values, which can be done analytically for Gaussian likelihood or with EP, Laplace, VB in case of non-Gaussian likelihood. But then we need to also integrate over the hyperparameters. One of the implementations of the automated statistician use this Bayesian information criterion, which just goes to the mode and look at the likelihood at the mode of the hyperparameters, and then just adds the BIC penalty term to that, which would work if there would not be prior, or it would be just a flat prior, and you saw that it's bad to have flat prior. And it would work if all the hyperparameters would be completely independent, but you also saw that especially the length scale and the magnitude have strong correlation. So it's fast to compute, but doesn't work well. Laplace approximation, you would go to the mode, compute the Hessian, so the mode of the hyperparameter marginal posterior would compute the Hessian there, and then use Gaussian approximation also for the hyperparameter posterior. This would take into account now the prior and posterior dependencies, but fails if the posterior is highly skewed, which it's likely to be. If you have sampled the hyperparameters, so you would for each model separately sample the hyperparameters or use CCD, you could compute the marginal likelihood estimate using the harmonic mean estimator, but it's for the marginal likelihood really, really bad. Usually has infinite variance, and the estimate mean doesn't exist, so you can get just anything out of that. So it seems there's computational problem then that how we would combine these models if we can't compute the marginal likelihood for the separate models easily, fast and accurately. There are then these different annealed importance sampling and thermodynamic integration and so on, but which take a lot of time to compute, which could get these marginal likelihoods more accurately. So there's Aki type weighting, replace margin, and so I start from the history because this was started, and in the literature you can find information about this with the googling Aki type weighting or Aki weighting. So replace marginal likelihoods with because the AIC, if it's using deviance, then you have the minus AIC divided by 2 there, and then it would be replacement for the marginal likelihood, and this is based on one vague sentence in 1970s paper by Aki, and there's no theoretical proof that it would work, and not even good simulation experiments showing that it's sensible thing to do. There are some simulation results so that those who like AIC, that model combination with these Aki weights is better than selecting just the best AIC value, which is not surprising. It's quite often any model averaging is better than just choosing one. Well, then since this Aki weighting has been so popular in statistics, when there was now the Watanabe came up with this fully Bayesian version of AIC, which really predicts the generalization capability of Bayesian models, so that you could then replace just the AIC with Wake, and because I think it's the Richard McElrath's book made this now popular. And again, it was just based on because that if someone is using Aki Wakes, we should be able to use these, but no real results for that. Then we have a paper, and so the Watanabe already shows that Wake and Leeuwenhout cross-validation are asymptotically equivalent. And then we had a paper showing that using the Pareto-smoothed importance sampling Leeuwenhout, you will get better estimates than using Wake. And that's what we then recommend using the Psyslu with Stan. And then some people started then to use XBLUE, now really being in the, not using the deviance scale, but using the log score scale. But again, people just started using it without testing, does it make sense? And it was kind of that, it was, I was objecting this, but because people started to use it more and more, then finally we had to write a paper where we also tested, does this work? So I show soon you results. What happens if we do this? But then instead of just starting from Akaike's comment about asymptotical results, we could start thinking about the actual decision problem we want to make. So we want to get good predictions, so we should think about that also when combining models, how to combine them to best good predictions. So maximize the scoring rule of the predictive distribution. So these are the predictive distributions for each separate model mk, so we have capital K models, and each model has a weight, and we combine them. So in a Bayesian model averaging, these weights would then be the posterior probabilities of the models, which are then related to marginal likelihoods of the models. Okay, so this is our combined predictive distribution, and the score is comparing it to the true data distribution. Since we don't know this true distribution, we use the usual mopen trick and use leave and out cross validation then to approximate that part. And then we can define stacking weights. And so let's go back here that we got the stacking name from the earlier literature, where instead of looking at the predictive distributions, they were combining, for example, predictive means, and then having some score to optimize so that weighting just the predictive means. And in our paper we saw that we can do that also for the predictive distributions. And so replace the PT part with the leave and out, and then we have these leave and out predictive distributions which are weighted, and the score function weights have to be larger than 0 and sum to 1, so that we can get also true distribution for the combination. When we use log score corresponding to Kullback library divergence, we call this stacking of predictive distributions. And so we maximize the weights so that these are the leave and out predictive distributions, weighted sum of them and log of that leave and out predictive densities, and sum over observations and maximize, and with the constraints. The example, so in our paper this was also that in a way we knew that theory says that optimal inference would be integrate over everything, and so in a way the Bayesian model average should be the optimal, but it's only optimal if one of the models is the true model, so-called M-closed case. And in that case also asymptotically, when we get more and more data, asymptotically that true model would get the posterior probability of 1. But what happens if none of the models is the true model? What happens with the Bayesian model averaging? So the simple example is that our model is just a normal distribution with mu and standard deviation 1. But now we have, so that just for a demonstration, we have different mu k's, discrete mu k's, correspond to this discrete set of models. We have different mu k's so that we have restrict them to be 1, 2, 3, 4, and 5 integer values. And now, what happens if the true value is 3.6? If we get more and more data, it happens asymptotically that in a Bayesian model averaging, the mu for gets posterior probability of 1, and it will make the model here. And so it's absolutely certain that mu is 4, even if the true value is 3.6. So of course now we had the model misspecification. None of our models was the true model, but it also shows that in this case the BMA can be misleading, that it still chooses one of the models when we get more and more data. It can't avoid it. Of course, this is can sound stupid, but why we restricted them to be integers? Why don't we have it continuous? But then with this automated statistician combining different kernels, we have again the case that we have discrete set of models, and we assume that actually none of the models really are the same process as like the Perth process in US. And yeah, how nice is that we can compute low efficiently for GPs, that we can do also the stacking for GPs. In the rest of the examples, I don't have GP examples, but something which is quite close, one example. So this is the Gaussian mixture example. So it was Gaussian mixture in that sense that when we now, each model itself was just a Gaussian, but now our combined model is a mixture of Gaussians with these weights. And with the BMA, it then just gets stuck on the 4. Stacking of means, we get something looking strange. Stacking of predictive distribution, it happens that it has weight, non-zero weight, also for model 3. And it's forming then mixture of models 4 and 3, which is then able to have the mode where the true data is. It is slightly wider. It can't, even when we get more and more data, it can't get exactly the same shape. But at least it can get the location better. And also based on the weights, we can see that it's probable that we don't have the true model in our models if we need to still weight more than one model with a non-zero weight. Here's how the log predictive density, so the predictive performance, goes when the n increases. So the log predictive density, stacking of means is really bad. Stacking of predictive distributions wins BMA. There's also for the mean square error and for the log. Okay, I'll skip that. The last one. Running out of time. This is linear subset regression example. What if we have lot of covariates and each model can use only one variable? How we combine that set of models? Here, these 4 plots, they have all the same lines. It's just that in different plots, different lines have been colored, so we can pick out, because there's so many lines, pick out important things. So here's the highest line is stacking of predictive distributions, so best performance. Next best is the Bayesian model averaging. Here, this dashed line is here in this paper it's called pseudo-BMA, and it's the one using Akaike-type weights using leave-one-out cross-validation estimates. So we see that it's worse than stacking, but it also has pseudo-BMA plus, which is almost as good as stacking of predictive distributions, which is a new idea that we can improve this leave-one-out weighting by taking into account the uncertainty in a leave-one-out estimate, as we should, as the Bayesians do. And then the lowest line is model selection by leave-one-out and model selection by marginal likelihood, and it's the worst. Same thing, that what if we choose k first variables? Again, stacking of predictive distributions, highest BMA, low, pseudo BMA, high. In this case, model selection by Lu happened to work also quite well, but the marginal likelihood model selection doesn't work well. Interesting is now in this stacking of predictive distributions that we can do this also even if the models are kind of from the strange source. Variational multimodal example. So the true distribution is multimodal. Variational inference has the property that in multimodal cases it can fit in just one mode, and as the KL divergence was in that direction, that it doesn't care about the error, it doesn't care that it's missing all this part. So it gets stuck in one mode. With another initial value, it gets stuck in another mode. And traditionally this has been a problem then, that how we combine these, because the probability that they find certain mode depends on an attraction area of this optimization algorithm, and that can be even fractal. And it's not clear also that then what are the kind of other errors, and so what's the difference between the masses. But then it turns out that we can use both the stacking of predictive distribution and pseudo BMA plus to combine then these results from different modes. Nonlinear model example, this was with splines, but this could be also with GPs. There's predicting rural Bangladesh whether someone switches a well, so that when some of the wells are contaminated by arsenic, and for the villages they will tell that, okay, now your well is has arsenic and it has this amount of arsenic, and then the next well can be in 1 kilometer or in 10 kilometers, and who is then switching based on the how much arsenic there is and how far the next well is, and whether they belong to some village association and so on. And then there were different type of spline models, and again this is kind of very close to this automated statistician thing then, that we are interested also getting explainability, interpretability in this wells example, and we can then compute the stacking weights, which will then tell also here this model has the highest stacking weight, and you can see that, for example, some of these models, they are already too flexible, uncertainty is quite high. These models were too strict, not flexible enough. And here's the model averaged results. And then the idea would be then that now we have the model average case, and then we could start checking that the projected model. So in M, open case works even better than BMA. The reference is in the end the slides. It's also likely, in our experiments we didn't focus on that, but it's also possible that even if we have M closed case, even if one of the models is the true model, it's possible that with small n, in finite case, this might be still better than BMA, even if asymptotically BMA will be optimal in M closed case. And so full model combining all possible choices, projection to a smaller model for easier interpretation and lower prediction cost. And there's references. Thank you. Yes?
Is it actually possible to infer discrete distributions instead?
How people have been using the model combination is that they do separate discrete models with Stan, and then they want to combine them. And then
That's not the Stan anymore, combination then?
yeah, it's now outside of the Stan, although, so we have the Stan-related loop package, which makes this combination. So that if you make the Stan models and you give the these log likelihoods to loop packets, it will give you the weights. So in that way, it's kind of the part of the Stan software, or even if it's in the separate package.
Will this be possible? I don't know, so like, let's say you just define some annuity distribution or whatever in Stan to infer this distribution then?
But now there was so Stan doesn't support discrete distributions, and it's quite likely that it's not going to support them for a very, very long time, because there's not similar theory for where to go in discrete space as what's for the Hamiltonian Monte Carlo. The Hamiltonian dynamics tell where to go. And of course there are then people making also the kind of the extra packages which use Stan inside and then discrete sampling outside. In many, many cases you can replace the discrete with continuous, or in many cases you can integrate over the discrete space analytically inside Stan code. So it's not that big problem. And then now when we see that in some cases, even if we could do the sampling over the discrete model space, it might be that we can get better results with this stacking of predictive distributions. And we also know that so there's also package using bridge sampling to compute marginal likelihoods for Stan models, so that you could do, using the bridge sampling, you could do this Bayesian model averaging over the models. But then again, as I thought, you might get better results with the stacking of predictive distributions. And of course, it's kind of for me, it was really hard that because the theory says that we should integrate over everything. and it was hard to believe that we could get better results with this stacking approach. Okay, then I was convinced that, okay, yeah, we can at least try with this case where we know that the true model is not included, that there it might work. But now I think that it can work also in that M-closed case, that because in a way I had thought too much about that, or I had forgot that the optimality of the Bayesian model averaging is only asymptotic optimality. And then in finite case, something else can work. And I'm happy that this is still decision theoretically justified approach. So it's not just ad hoc.
You said when there are two modes or many other modes,
Mm-hmm.
and the model gets stuck, you said that you combine the possible solutions of each mode. I was just wondering about the mixture. You know how to unify those models. It's not to, for me, Gaussian mixture model, something like that. You have the responsibility of each model. So how do you weight each model to give the correct weight to explain data?
So it was the stacking which gives the weights. So we optimize the weights, that what combination gives the best predictive performance estimated with leave-one-out cross-validation.